Okay, 7.2.4. Now, test statistic. What do we mean by test statistic? Never mind, I will just explain. Remember, we always say if X bar follow a normal distribution 30, this is if H naught is true lah. If H naught is true, then X bar follow a normal distribution. This means it's because H naught is true. If H naught is not true, then this means it's not true. Then we say, oh, okay, this is a bell curve. Then this is 30. Then because I decide on the level of significance 5%, therefore, I will have a decision making 34.9 critical value. Now, if I write it like that, then what is the test statistic? The test statistic, remember, at the start of the lecture, I talked about using a sample statistic to make a decision. And the decision was whether the mean is 30 or not. Now, so therefore, the test statistic we are interested in is not the variance, it's not the whatever, it's actually the X bar. It's the X bar. X1 plus X2 plus X3 all the way X9 divided by 9. So, whenever in hypo testing, when we say test statistic, we could mean X bar. Then we say, oh, okay, X bar is a random variable. Then we compare our small X bar. That means this is the sample mean by calculating. This is sample mean by calculation, right? By really sampling. Take 9 times, order pizza 9 times, and then divide by 9. This, in the end, I get 38.2. Then compare this against my critical value of X bar. That means this one. Right? Then we say, oh, okay, I compare 38.2, compare greater than 34.9. Okay, in the rejection region, reject. That is one way of looking at the test statistic. Now, but very often in statistics textbooks, we don't use X bar as the test statistic. Why? I tell you later. Okay? But now I tell you what do statistics textbooks usually say. If H naught is true, still the same thing, X bar follow a normal distribution. More importantly, if I take X bar minus 30 divide by square root 9 square over 9. What is this thing? Do you all know? Standard normal. Correct? Standard normal. I can standardize my X bar and then I say this is standard normal. Now, very often we use the standard normal Z as the test statistic. Now, which is nothing very different except that I just normalize it. Do you know what I'm saying? I just normalize it. So then I can still draw my bell curve. If X bar is true, then it must be a standard normal. Then I say this is 0. Can I still use... I definitely must use my 38.2 to make a decision. But I don't use it like that. I will say, okay, because I want my rejection region, because I want level of significance to be 5%, right? I still want that, same. I can still calculate what is this critical value. 1.6449. Then you ask, how can this 38.2 compare against this one? Cannot be, right? It's not apple and orange, how to compare? Follow what I'm saying? But this is X bar minus 30 divided by square root 9 square over 9. Then you get Z, right? This is like that, right? So in order to compare 38.2, later on I'll explain. So now, this time your test statistic, I jumped a little bit, is correct. This is now my test statistic. How then do I compare 38.2? I will not compare 38.2. I will compare the transform value of 38.2. I compare the small z, that means I take 38.2 minus 30, divide by square root 9 square root 9. Follow what I'm saying? Then I just compare the same. Actually, it's no different. I just compare different things. Of course, I'll end up the same conclusion, right? I will still end up in the rejection region. Does it make sense to all of us? You will end up here. Now, it doesn't make sense to all of us that if this one 38.2 lie in the rejection region here, this 2.73 must lie in the rejection region. Sure. But then you see, so why so troublesome when transform? Correct, I myself do this. Follow what I'm saying? Myself do this. I agree to it to a certain extent. I'll give you two quick reasons why most statistics textbooks use this. First reason, you do many tests, correct? You sometimes do design, you sometimes do height, do weight, etc. Every time you do a different test, the mean is different. Then therefore your critical value will always be different for different tests. Now for standardization, we want to have, but if we use standard normal and we use the same level of significance, 5%, this 1.6449 will always be the same. Follow what I'm saying? And the second reason follows the first reason. The second reason is that last time, no GC. When I took my A levels, there was no GC, there was a normal distribution table. You cannot inverse norm like that, this one, I don't know how to inverse norm, there is no GC to help me. You have a normal distribution table. You go back and take a look. You go and search online, MM15, the full MM15 that you see in your CP2 paper, CP2 exam, you always take MM15 and you see all the way to the back, there is a normal distribution table that help you inverse norm 0.95 for standard normal. Nobody can help you do this. Table won't do this because you have mean 30, mean 40, mean 50, mean 51. Where does it end? You follow what I'm saying? So because there was no GC to help us, we all rely on the table. It's all easier if we standardize everything. You get what I'm saying? All right. So those are the two reasons. And really for simplicity, usually throughout the whole chapter, I will use this idea. Test statistic is the transform value x bar minus mu divided by variance. There was standard deviation, sorry. Follow? But I think the idea is the same. If you can understand this, this is just transform. So far so good. Okay, cool.